Information security often depends on invisible foundations: the power that keeps servers alive, the air conditioning that prevents overheating, and the cables that silently transmit data across networks. These elements rarely appear in policy discussions, yet they underpin every digital process within an organization. When these foundational systems fail, secure operations can grind to a halt in seconds. Annex A.7.11 and A.7.12 of ISO-IEC 27001 address precisely this hidden layer, emphasizing the resilience of supporting utilities and cabling. Both controls remind organizations that physical infrastructure is not a background concern, but an integral part of availability and confidentiality. By designing for resilience at this level, an organization prevents downtime, data loss, and cascading failures that can compromise security objectives. The scope of Annex A.7.11 covers all utilities that sustain ICT and security systems. Electricity, heating, ventilation, air conditioning, water, and telecommunications all fall within this category. Each utility contributes directly or indirectly to operational stability. If power fluctuates, servers may crash. If cooling fails, hardware can overheat. If communication lines go down, monitoring systems and response teams may lose visibility. The objective of this control is to ensure reliability through a combination of preventive and reactive measures, preventing outages where possible and minimizing impact when they do occur. Documentation of these safeguards helps verify that resilience is not left to chance. Electricity and power continuity are often the most visible aspects of utility resilience. Critical systems rely on uninterruptible power supplies, or UPS units, which bridge the gap during outages or voltage fluctuations. Backup generators provide longer-term continuity, but only if they are regularly tested and supplied with adequate fuel reserves. Surge protection guards against grid instability and lightning strikes, preserving sensitive electronic components. Advanced monitoring systems now track power quality and detect early faults, enabling proactive maintenance before small issues escalate. In combination, these measures ensure that even during external utility failures, the organization's essential services remain operational. Environmental stability, maintained through HVAC systems, plays a similar role. Cooling infrastructure must be carefully sized to match the heat load of servers and storage systems. Redundant air handlers prevent hotspots and allow maintenance without downtime. Humidity regulation protects both electronic components and magnetic media from static discharge or corrosion. Documentation, such as maintenance logs, not only proves compliance, but also extends equipment life and warranty support. When HVAC systems are neglected, even minor temperature variations can trigger performance degradation, drive errors, and unexpected shutdowns. Telecommunications resilience ensures that connectivity persists despite disruptions. Many organizations maintain contracts with multiple service providers, creating failover routes that automatically reroute traffic if one carrier experiences an outage. Service-level agreements can guarantee rapid restoration times during incidents. Continuous monitoring detects degradation before it becomes a full outage, while secure routing and encryption protect communications from interception or tampering. These safeguards maintain operational continuity and uphold the integrity of data flowing between facilities, partners, and users. Water and fire suppression systems introduce a delicate balance between safety and risk. Water leaks from overhead pipes or nearby restrooms can devastate server rooms in minutes, while poorly chosen fire suppression systems can cause collateral damage. The recommended approach uses non-water suppression agents, such as inert gases or dry chemicals, in critical spaces, avoiding the hazards of traditional sprinklers. Regular inspection of valves, pipes, and emergency shutoffs ensures reliability when emergencies occur. Testing these systems under controlled conditions validates performance and minimizes the chance of a double disaster, when the safety system itself becomes a threat. Demonstrating compliance with A.7.11 requires tangible evidence that supporting utilities are both robust and well-managed. Organizations should maintain contracts with utility suppliers that outline continuity expectations and escalation procedures. Logs of UPS and generator tests show readiness for power disruptions. HVAC and suppression systems should have documented inspection cycles, maintenance records, and calibration data. Infrastructure diagrams displaying redundant paths for power and communication help auditors visualize resilience at a glance. These records collectively prove that the organization not only planned for resilience, but actively maintains it. History shows how quickly these unseen layers can cause visible damage. A data center in a financial exchange once experienced hours of downtime because a backup generator had never been fully tested under load. Another facility lost millions in hardware after a cooling compressor failed during a heat wave. Government offices have suffered data loss due to burst pipes in ceilings above server rooms, while telecom firms have been hit by simultaneous outages from dependent carriers. Each incident underscores that security and resilience share a common root: reliable infrastructure. When organizations treat utilities as strategic assets rather than background services, they move closer to genuine operational maturity. Annex A.7.11 makes it clear that availability, one of the core pillars of information security, begins with stable energy, controlled climate, and dependable communication. Without these, encryption and access control mean little, as no system can function without power, air, or connectivity. A resilient ISMS recognizes this interdependence and embeds physical infrastructure considerations into its core design. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Annex A.7.12 shifts focus from utilities to cabling, the veins and arteries of the information infrastructure. Power and data cables form the unseen pathways that carry both energy and information, yet they are often overlooked in security planning. This control exists to protect those pathways from threats, such as damage, interference, or deliberate tampering. Its scope includes everything from the cables running beneath raised floors to external lines entering a building from the street. The intent is to preserve both integrity and confidentiality of communication by ensuring that cabling is properly designed, installed, and maintained. When the underlying network is physically secure, digital defenses stand a far better chance of holding firm. Effective cabling security begins at the design stage. Power and data lines should be routed separately to prevent electromagnetic interference, commonly referred to as EMI, which can degrade signals or even cause data corruption. Concealed conduits or structured trays keep cabling organized and shielded from accidental contact or impact. In high-risk areas, such as public corridors, armored or shielded cabling provides additional protection against cutting or tapping. Patch panels, termination racks, and distribution points must be physically secured, ensuring that only authorized personnel can connect or disconnect lines. These design considerations create resilience by removing easy opportunities for disruption. Access control remains essential throughout the cabling environment. Only trained technicians should have permission to enter areas where cabling infrastructure is exposed. Locks or tamper-evident seals on junction boxes and cabinets prevent casual access and signal any unauthorized attempts. Maintenance activities should be logged, detailing who accessed what area, when, and why. In highly sensitive facilities, video surveillance or CCTV coverage may be positioned to monitor key termination points. These precautions transform cable management from a technical chore into a controlled process that supports auditability and accountability. Monitoring and testing reinforce these protections over time. Regular visual inspections help identify frayed insulation, loose connectors, or early signs of interference. Certification of new installations ensures that they meet both electrical and communication standards before going live. Detection systems can alert security teams if an unauthorized connection or signal deviation is detected, indicating potential tapping or damage. Fault isolation tools allow technicians to trace problems quickly and document the results for quality assurance. Together, these measures create a proactive approach that detects small issues before they cascade into outages or breaches. The risks tied to cabling are both accidental and intentional. During facility renovations or maintenance, an unmarked cable might be cut, causing unexpected system downtime. In shared buildings or multi-tenant data centers, attackers may attempt to intercept communications through exposed fiber runs. Poorly separated power and data cables can introduce interference that weakens both system reliability and security monitoring. Overloaded cable bundles present fire hazards, especially when combined with insufficient ventilation or improper insulation. Recognizing these diverse risks highlights why cable management belongs in the same security conversation as firewalls or encryption. Auditors evaluating A.7.11 compliance look for structured documentation and operational proof. Cabling diagrams should clearly show routes, conduits, and protection methods, demonstrating awareness of critical pathways. Inspection and testing reports, dated and signed, show that maintenance is both routine and methodical. Access logs record authorized maintenance events and any incidents of deviation. Records of cabling-related disruptions and how they were resolved demonstrate that the organization not only installs controls but also learns from experience. This traceability creates confidence that cabling security isn't theoretical but operationalized. Real-world examples illustrate why attention to cabling matters. A global data center once suffered a complete outage when a contractor accidentally severed an unmarked fiber link feeding its core routers. In another case, an industrial facility experienced data corruption traced back to electrical interference caused by overlapping power and data conduits. Telecommunications operators have found deliberate tapping devices attached to exposed exterior cabling in remote junction boxes. Even office environments have seen fires originate from cable bundles overloaded with unauthorized extensions. Each case shows that cables, though passive components, play an active role in an organization's security resilience. Integrating cabling security into infrastructure planning offers long-term benefits beyond compliance. Well-organized cabling reduces downtime during upgrades or relocations, making maintenance faster and safer. Documented routes prevent accidental damage during construction or expansion. Security by design also simplifies incident response. Knowing exactly where lines run allows teams to isolate faults without guesswork. These operational efficiencies translate into reduced costs and improved reliability, demonstrating that physical protection and business value can coexist naturally. When combined, Annex A.7.11 and A.7.12 establish a comprehensive foundation for physical infrastructure resilience. Supporting utilities deliver stable power, climate, and communication, while secure cabling ensures that data flows safely through those systems. Together, they minimize the likelihood of outages, tampering, and interference. This alignment between energy, environment, and connectivity reflects a mature understanding of how physical and digital domains interact. An effective ISMS recognizes that every bit of data depends on these physical threads and designs accordingly. Organizations that apply these controls rigorously create visible evidence of maturity in their infrastructure management. Redundancy diagrams, inspection logs, and access controls become living artifacts of good practice. Visitors, auditors, and even internal teams can see professionalism in how cables are routed, how utilities are documented, and how systems continue operating smoothly despite challenges. This visible discipline reinforces confidence across stakeholders, from IT operations to executive leadership, that security is not an abstract concept but a tangible reality. Ultimately, Annex A.7.11 and A.7.12 anchor an organization's information security management system in physical reality. They remind us that cyber resilience depends as much on air conditioning and power lines as it does on passwords and firewalls. By securing utilities and cabling, organizations strengthen the unseen foundations that every other control relies upon. When these layers are designed, maintained, and monitored with the same rigor as digital systems, the result is an environment where reliability and security reinforce one another, forming the quiet architecture that keeps information flowing and operations alive.